So hello everyone. Today we shall discuss the last topic of this module, which is on the structures for the discrete time systems. So to discuss about the structures for the discrete time systems, we had seen in the past couple of lectures the design and analysis of some of the discrete time filters, how you can achieve the either you convert them from the continuous time or you design from the scratch, but ultimately you have to implement those systems or manufacture those systems through some hardware architecture, which is generally implemented with some VLSI technology. Okay, so starting from the basic difference equation, let's see, we are given some difference equation y of n as a1 y n minus 1 plus a2 y n minus 2 plus b naught x of n, where xn is the input of the system and yn is the output of the system. And this difference equation governs the physical laws described by the system. We had seen earlier that we can also compute the Z transform for this difference equation, which I can write directly as b naught upon 1 minus a1 Z inverse minus a2 Z to the power minus 2. So generally we use the block diagram representation. There are other representations also, for example signal flow graphs, but we will not dwell into the signal flow graphs. We will see that what are the different forms of representing this equation through some block diagram, and what is the physical significance behind different block diagrams. So if I want to implement this difference equation through some, or let's say if I want to realize this difference equation through some block diagram, I can use that xn as the input multiplied by the scalar gain b naught, and let's say it gives me yn, and then I can build my structure. So in this structure, what do you notice? That this block diagram realizes the above difference equation. So this y of n is here, and once it travels through the z inverse path, the input at this the output of this z inverse block would be yn minus 1. And once again, once if it is passed through the z inverse block, the output of this block would be yn minus 2. So if you see this difference equation once again, this y of n is basically the summation of these three quantities, a1 times y of n minus 1. So we have this a1 scalar gain multiplied by yn minus 1, and it sums up to yn. Similarly, a2 times yn minus 2 sums up to yn. And finally, the feed forward term b naught times x naught contributes to yn. So this is, in this simplistic way, you can realize this difference equation through some block diagram. You can also generalize this block diagram representation for some higher order system. Let's say the high order difference equation is given by y of n minus summation of k 1 to n ak yn minus k is equal to summation k is equal to 0 to m bk xn minus k. Okay, seeing the Z transform representation, it can be represented by k is equal to 0 to m bk z minus k and 1 minus summation from k1 to m ak z to the power minus k. Okay, so to realize this higher order difference equation, let's say what we first of all, let's substitute this part as v of n. Then my difference equation can be written as y of n is equal to summation of k1 to n a k y n minus k plus v of n, where v of n is this term. Now this difference equation can be realized through this block diagram representation. Okay, let's focus on to this part. So here your auxiliary variable v of n, which we have introduced. So all the terms starting from xn delayed up to n minus m multiplied with their respective scalars from b0 to bm and then contributes to vn. This is how we have written vn, because vn was given by the summation of k0 to m bk times n minus k. Okay, so all these respective coefficient multiplies by their corresponding delayed input signal, which summed up to give you vn, and then vn is then add up to the rest of the term, which is a recursive term basically. So all these delayed version of yn multiplied by their respective scalars would add to give the final difference equation y of n plus v of n. So this is only just one representation, one block diagram representation of the difference equation. Now if we see from the frequency domain representation, there could be many other, in fact there could be infinite block diagram representation. Say for example, this frequency domain representation or Z transform representation I can represent as the multiplication of two frequency domain representation h1z and h2z, where my h1z is the term which is in the denominator with 1 in the numerator. So 1 minus summation of k1 to m ak z to the power minus k, and the remaining numerator term, which is the summation k is equal to 0 to m bk z to the power minus k. So this is my h1 and this is my h2 of z. So the representation what you had just seen, I had substituted my Vz, which is the frequency domain representation of the signal Vn, as h1z times x of z, where x is the input. So my excuse me, so here there's a minor typo. So this we had substituted as h2 of z, and this we had substituted as h1 of z, and we have represented v of z as multiplication of h1z times the frequency domain representation of the input signal x of n. So h1 of z is, if I replace this by k, bk z is minus k, and xz is this one. And finally my yz is given by h2 of z times v of z. So if you see the overall block diagram, the frequency domain representation, it remains the same as it is. And this is the idea behind realizing all the difference equation with some block diagram representation. So this is what we had. This is for this decomposition we had seen the block diagram representation. But now if I use if the the different decomposition in the form h of z as h1 of z and h2 of z, where my h1 of z and h2 of z remain the same. So this vector comes here and this vector comes here, and now instead of using this equation I define another auxiliary signal, say for example w of z. So that w of z I can write as h2 of z times x of z, where my h2 is a rational function and h1 is my polynomial of z. And finally I write my y of z as h1 of z times w of z. So what it will yield finally, h1 of z, h2 of z times the frequency domain representation of the input signal. Okay. Now if we see the block diagram representation, it is given by this one. So there is some minor changes. This is the representation where we have used v of n, and here in this block diagram representation we have used w of n. So the position of the integrators or the delays, are changed from the previous representation. Right? For the same auxiliary signal w of z, you achieve the same rational function with this block diagram representation. You can calculate by yourself, in the sense that it is basically the combination of these two delays into one delays. So a quick difference what you notice in this representation from this representation is that the number of delay blocks are reduced to half than this representation, right? So different block diagram representation, different computational complexities, because ultimately you have to implement these difference equations or the discrete time system onto some chip using some VLSI technology. Okay, so all these other blocks, the delay blocks, the multiplication blocks or the convolution blocks, the summation blocks, the subtraction blocks, they all contribute to the computational burden to compute the output for some given input. But the ultimately objective is whatever the block diagram representation you use, they should give you the same rational function or the same the discrete time system. So different block diagram representations, different complexities in terms of the computational burdens. Similarly, there are many algorithms also by which you can achieve or can realize some discrete time system in some optimal sense. There are several algorithms. Okay, there are other quantification factors in the terms of ease of implementations. So we will not dwell much into how to compute the computation burden onto some chip or of some block diagram representation and what are the different algorithms. But here we will see only the basics, that a particular discrete time system could have very nice properties, and we had seen they can be uniquely represented by a difference equation or the rational functions. But when it comes onto the implementation onto some chip, then there are infinite choices depending on what is your objective. Okay, and there are several factors associated with it, which is the next step, which comes for the which you will study mainly in the advanced DSP courses. Like what are the different algorithms, what are the computational complexities of different algorithms, the computational burdens associated with some particular representation. So this is the basic idea. Okay. Now the next important thing which we will carry out in this module is about the window functions. So what are the windows functions and what are their significances? So before coming on to analyzing the window functions, we will motivate it through that why do we need them. So in the past, or let's say we have defined two classes of the filters. One which is of the IIR filter designs, infinite impulse responses systems, and another is the FIR, finite impulse responses filter designs. So we had seen one design technique for IIR filters which are defined by some rational functions. Okay, but these window functions we generally use for approximating the FIR filters. And we'll talk about it a bit in detail a bit later. But let's see, first of all, some nice properties associated with the IIR filter design so that we can motivate more about the window functions for designing the FIR filters. So these IIR filter designs generally relies on the transformation of the continuous time filter to discrete time filter, meeting some prescribed specifications. Okay, so this one of the technique we had seen in the past, if you recall, that where we have used some cascaded block diagram representation uh, to approximate the continuous time behavior or through some discrete time, or to realize the discrete time system through some given continuous time filter. So the impulses, so the first thing is they're designed by impulse invariance. So this is the technique we had seen. Let's see quickly that what we just recall what we had done there. So the impulse response of the discrete time filter is chosen proportionally to equally spaced samples of the impulse response of the continuous time filter. Let's say a continuous time filter is given to us. Let's represent it by h of c. So we sample this hc, equally sampled td. Scaled version of this, we design the impulse response of the discrete time filter. So this td is the sampling interval, which is generally no role but just for the mathematical technicalities. Okay, we use this equation. Okay, where hc is some given continuous time filter. Why generally, if this question arises into your mind, that why do we relies on, or why IIR filter design rely on the transformation of the continuous time filter to discrete time filter? Because there are many techniques which are very well nice structured for designing the continuous time filter. So by using those techniques and by using and further using some transformation which we will see very quickly now, we can realize a discrete time filter which is having an infinite impulse response. The objective of having the prescribed specifications, that what should be the cutoff frequencies, the pass band, and the stop bands in the frequency response, all those specifications would be met. We will see that very quickly now, that under what circumstances those specifications will be met and under what circumstances those specifications would be met. Okay, so starting with this impulse variance representing the impulse function in relation to the given continuous time impulse function. We can also represent them in the frequency domain as e raised to the power j omega is equal to the summation from k minus infinity to infinity of h of c j omega by td plus j 2 pi by td k. This we had seen already. We are just quickly recalling that what are the different transformation functions. So if the continuous time filter is band limited, so that you have hc of j omega is equal to 0 for mod omega greater than or equal to pi by td, then in that case I can represent my frequency domain representation of the discrete time function h of e raised to the power j omega as hc of j omega by td. Okay, so the nice property what you see here is the linear scaling of the frequency, which is omega is equal to continuous time omega times td for mod omega less than pi. So this is the linear scaling, which is the nice property associated with this impulse invariance if we design the IR filter using this impulse variance. So here one of the assumption here is that the continuous time filter should be band limited, but unfortunately any practical continuous time filter cannot be exactly band limited, right? But if it is not band limited, then it would definitely cause the aliasing, which we had studied in during the sampling when we were discussing about the sampling theorems and techniques. Okay, however, if the continuous time filter approaches 0 at the higher frequencies, the aliasing may be negligibly small. Okay, so still you can carry out this design procedure if your continuous time signal is not band limited, but at least at higher frequencies it approaches to 0 relatively than the lower frequencies. So we can quickly see now, assuming that the aliasing involved in the transformation from hc of j omega to h of e raised to the power j omega negligible. Let's say some continuous time rational function is defined as some summation of k is equal to 1 to n ak upon s minus sk. Here s is the Laplace transform variable and sk is the location of the pole, right? So s is the Laplace transform variable and z is the z transform variable. Okay, so this frequency domain representation or the Laplace transform basically is of the function which is defined in the continuous time in the time domain as summation of k 1 to n ak e raised to the power skt for t greater than 0 and 0 for t less than 0. Okay, now using that relationship, this relationship by which we realize or we design the IR filter is that h of n is equal to td times hc of n td which I can write as by replacing this with the HC function above, k1 to n td times ak times e raised to the power sk and td u of n, where u is the unit step function. Okay, or equivalently I can write this as summation td ak e raised to the power std n un, so sk, excuse me, sk. So in this, now you can see I can now write the z transform representation of this h of n. H of z as equal to summation from k is equal to 1 to n td time ak divided by 1 minus e raised to the power skt z inverse. Excuse me. Okay. So one important thing to note here, that the pole at the location SA in the continuous time domain in the S-plane transforms to a pole at z is equal to e raised to the power SKTD. This one. Okay. So this is a straightforward transformation from the continuous time continuous time frequency domain representation to the discrete time domain representation in terms of the transformation of the poles. Right? This does not hold valid for if you want to map the zeros directly from the continuous time to discrete time. Okay. Another important thing, that in this procedure, the relationship between the continuous time and discrete time frequency is linear, which is the very nice property of it. Okay, so consequently, except for aliasing, the shape of the frequency response is preserved. Whenever you analyze the frequency responses, the plots of the frequency responses, the three plots what we had seen earlier, the magnitude plot, the phase plot in terms of the principal value, and also the group delay plots. What you will notice, that the shape of those responses are preserved when you convert the continuous time domain to discrete time. Right? But of course you would see some aliasing, but it can be avoided. So there is another type of transformation which we say as the bilinear transformation. So unlike the previous transformation, so this transformation is non-linear in nature, where we map the continuous time frequency from minus infinity to infinity to omega lying between minus pi to pi. So this transformation is non-linear, and the function we use as s is equal to, so s is replaced by s 2 by td times 1 minus z inverse upon 1 plus z inverse, which gives that your h of z can be represented as your hc replaced by 2 by td 1 minus z inverse upon 1 plus z inverse. So this is how you can use this bilinear transformation to synthesize the IIR filter. So with the help of this, you can design many other filters, Butterworth filters, Chebyshev filters, right, by using these transformations from the given continuous time filter. Okay. So now, so these are the two basic types of transformation. In fact, in the literature, there are many other types of transformation with their respective properties. So, but these two are the basic one which you can use majorly. Right. Now, moving to the now we can safely move to the windowing functions. So, in this window functions, what do we do? That the idea is to synthesize the FIR filter responses or the FIR filter systems. Yeah, just a minute. So there is one topic left before this, before we come on to the window function. So this is a very small topic, but it is good to recall, which we say that the frequency transformations of low pass IIR filters. The point of discussion under this subtopic, that given a low pass IIR filter, we want to transform it to obtain other types of filters: high pass, band pass, band stop filters. Okay, so there is some direct transformations. Once you have synthesized the low pass IR filters, you can transform them to actually yield the high pass, band pass, and band stop filters. Okay, so let's see quickly what do we mean by this thing. So in this figure, you see the x-axis as the frequency and the y-axis is the magnitude of the filter. So here you see three bands, one which is before this omega p1, and the magnitude varies from around the unity gain of plus minus 1 delta. There is another band from omega s1 to omega s2, and the magnitude is around delta 2. And finally, there is another band from omega p2 to pi, which again varies around 1 of plus minus delta 1. So generally this is how we define the tolerance limits for a multi-band filter. So let's say if you have if you want to design some low pass filter, so it would be something like this. The frequency response would be like this. If we want to design some high pass filter, it would be something like this. Now if we want to design some band pass filter, it would be something like this. And similarly some band stop, this and this. Okay, so all types of filters you can nicely, this figure particularly gives you the tolerance limits. So now if we want to design the other filters, given a low pass filters, this transformation table you could use. This transformation table is generally available in the, I will upload the lecture notes as well. We won't go into the mathematical details of this transformation, but we will try to cover one example through which you can see that how these transformations are useful and what is their impact and what is its impact onto the desired objective of achieving some filter responses. Okay, so here this theta p theta p, what you are seeing, theta p is the cutoff frequency of a low pass digital filter prototype from which we want to transform it to some other desired cutoff frequencies defined by omega p. So this low pass is also, again, if you want to change the cutoff frequencies of the given low pass IIR filter. Okay, high pass we had seen how the filter response would look like. Band pass would have two desired lower and upper cutoff frequencies, and similarly band stop would also have some lower and upper cutoff frequencies, and these are the transformations from discrete time domain to discrete time domain for achieving the other types of filter responses. Okay, so let's see. Let's say we want to let's consider one example. So here in this example, some type 1 Chebyshev filter, low pass filter is given to us. Okay, whose system function is defined by HLP Z. I'm using the capital Z here so that it would be easier for us to, because this filter we are considering as a prototype filter. Okay, so this filter is given by 0.001836 1 plus capital Z inverse to the power 4 and some two polynomials in the denominator as 1 minus 1.5548 Z inverse plus 0.6493 Z raised to the power minus 2, 1 minus 1.4996 Z raised to the power minus 1 plus 0.8482 Z raised to the power minus 2. Okay, so suppose this fourth order system was designed to meet some specification, and these specifications are given as that the magnitude response of this j theta is lying between 0.89125 to 1, for theta lying between 0 to 2 pi, 0 to 0.2 pi. Okay, and HLP raised to the power j theta for higher frequencies, it is less than 0.17783 for theta lying between 0.3 pi to pi. Okay, so these are the desired specification onto this filter. Now if we see the frequency response on this filter, this is how all the three responses would look like. This is a low pass filter where it passes the frequencies within its band from 0 to 0.25, and afterwards 0.0235 it is less than 0.17783. Okay, this is the phase response in terms of the principal frequencies, and this is the amplitude. Yeah, this is in dB, but this is in your magnitude. This is in the log magnitude, and this is the absolute magnitude, and finally this is the group delay. Right? This is how the response of this filter look like. Now carrying out our desired transformation, and we want to transform this filter into some high pass filter with pass band cutoff frequency. Let's say write the desired high pass filter, pass band cutoff frequency is 0.6 pi, and now using the formula in the previous table. There are two design parameters. Alpha is minus cos, this is theta 0.25, another parameter which comes from the given low pass filter function or the characteristics, plus 0.6 pi divided by 2 divided by cos 0.2 pi minus 0.6 pi divided by 2, right? So this alpha is computed as 0.38197 with a negative sign. Okay, now from the formula we compute this h of z for the given h of capital Z, this low pass h z. When I substitute z inverse as minus of z inverse minus 0.38197 divided by z inverse, divided by 1 minus 0.38197 z inverse. So if I replace my capital Z inverse by this formula, I would obtain, so it is expected that you will obtain the function for the high pass filter. So putting this, you will obtain your h of z as, I'm just writing for you to verify it later, you can do it 0.02426 1 minus z inverse to the power 4 1 plus 1.04 16 z inverse plus 0.4019 minus 2 . So again this is a fourth order transfer function. So if we see all the plots for this function, this is how they look like. So now this is the log magnitude plot, this is the absolute magnitude plot, and this is the group delay. So you see that in this example you see the equiripple pass band and stop band behavior, okay, is completely preserved by frequency transformation of this type, right? So in the earlier one we were having the ripples here, and finally the ripples would again appear in the pass band. So the ripples in the pass band are completely preserved in this transformation. Okay, so this is how you can achieve the transformation. Okay, so now we can finally move on to our last topic for this module as the window functions. Which is basically used for the design of FIR filters by windowing. So IIR systems, you see that the continuous time IIR system is transformed to discrete time IIR system. For FIR system, we approximate the desired frequency response of the discrete time system, right? So let's say some desired frequency response is given by some hd e raised to the power j omega is equal to the summation of n minus infinity to infinity hd of n e raised to the power minus j omega n. Okay, hd of n you can write by the formula we had seen earlier, 1 over 2 pi from minus pi to pi hd e raised to the power j omega n. j omega n d omega. So synthesis and the analysis equation of the Fourier transformations. Now what do we want to do? We want to implement the finite impulse response. So we will truncate this hd of n by approximating it so that it would give us the filter function approximating the same type of specifications. So h of n we define as hd of n for n lying between now 0 to capital N, otherwise it's 0. Okay, or we can write h of n as hd of n multiplied by some function wn, and this wn we define as the window function. Okay, so let's recall from one of the properties of the Fourier transform, which we call the modulation or the windowing theorem. We know that if there are two time domain functions being multiplied, then I can write the frequency domain representation as 1 over 2 pi minus pi 2 pi hd e raised to the power j theta times w e raised to the power j w minus theta omega minus theta, sorry, d theta. By the way, when I write or, so this omega n can be defined as 1 for 0 to n lying between 0 to n and 0 otherwise. Okay, a simplistic window function. So what does it say? Basically it is you are kind of computing, it is a periodic convolution of the desired ideal frequency response with the Fourier transform of that window. So thus the frequency response h of e raised to the power j omega will be a smeared version of the desired response. Let's see the typical filters. Okay, so pay attention only to the figure A. We will come on to this figure B. First of all, pay attention to this figure A where this is some desired by some desired impulse function, and this is the representation of the window function, right? And they are defined as the function of theta. Okay, now let's say so if we see explicitly this, let me write it here so that it would be easier for you to visualize. Let's say if I write the Fourier transform of this window function alone, which is a simplistic rectangular function of which I can write as n 0 to m, which is 1 e minus j omega n, right? So this is defined as 1 minus e raised to the power minus j omega m plus 1 divided by 1 minus e raised to the power minus j omega, or taking e raised to the power j omega m by 2 common as sine of omega m plus 1 by 2 divided by sine of omega by 2. Okay, this is your w of e raised to the power j omega for that simple rectangular function. Now see this figure 7.8. This is basically your magnitude of the Fourier transform of a rectangular window when I put m is equal to 7 in that formula. So what do you see? That most of the The highest magnitude you observe around this part and here, and this almost closer to 0. Again you observe the same behavior at 2 pi. The main point of interest are the frequencies at these 2 points, and this we call it the main lobe width, which is of delta Wm, and these are the peak side lobes. Okay? And the properties associated with it, that the area of this lobe remain the same. So if you increase the width of the lobe, the peak of the lobe would decrease, and vice versa. Okay? And once we smear this W over this H, this is how I would obtain the overall H of e raised to pi j omega if I do the convolution of this HD and this W. Right? The important thing you notice here, in fact we had discussed this earlier as well. If you recall, about we have discussed about this Gibbs phenomena, that at the point of discontinuity you will see the oscillations, right? And as you increase the value of m, the oscillations would be reduced here, but it will be oscillating uh, at the point of discontinuities. So this is the basic phenomena you would generally observe. So this is how you can approximate the FIR filters. So this is one of the windows. Now there are many other windows functions which are used in the literature: Hamming window, Hand window, Blackman window, or Bartlett window. They are defined by uh, different functions, of course, but the idea of all them, that there some nice properties are associated in terms of the frequency response when you multiply the time domain representation with the desired frequency response, right? So this is the overall idea of the window functions, that for the given the desired impulse function, how we can approximate it using some FIR filters by using this window function. The design of IR system is pretty much straightforward, that we generally transform them from the continuous time to discrete time. Once we have designed the low pass IIR system, again we could use another transformation table to compute the other types of filters, and one of the examples we had seen. Okay, so I think we can stop here today. Thank you.